Hi, I'm Dr. Matthew Michal. I'm a lecturer of mathematics at NJIT in Newark, New Jersey. I've been talking about differential equations, specifically some of the work through Boyce and DePrima's textbook, the 10th edition. These are mostly to help you understand what I'm thinking, what others are thinking when we talk about these subjects from a mathematics point of view. Today we're going to talk about variation of parameters, a slightly more complicated but safer version for solving non-homogeneous differential equations. This is not to say that the method of undetermined coefficients is not safe, but it is this way, assuming you do your mathematics correctly. You're not guessing. You're not trying to estimate what the form might be. The form will automatically give you the right answer. For this, we're going to go through the solution of the textbook case and then end the lesson with a formula that you can use and that you can just plug in. I'll try to talk you through how this works for this particular problem, since we don't have an example for that formula, but this will be a little bit on the short side. So, last time we talked about undetermined coefficients, how we can guess or estimate or determine what the form of the solution would be based on the right-hand side of the differential equation mixed with the complementary solution of the homogeneous differential equation. For variation of parameters, we're going to need to know the homogeneous answer just like before. However, unlike last time, we're not going to need to assume anything about the right-hand side. That's going to help a lot. As long as we put it in this form, make sure that there are no coefficients in front of y double prime. That will mess everything up, even if you happen to forget, say, a 2. No constants, no functions, nothing in front of y double prime other than 1. I cannot stress this enough. Okay, so let's use this as a textbook case. Well, it technically is from the textbook, but you know what I mean. Y double prime plus 4y is equal to 3 cosecant of t. This is literally impossible to use for the method of undetermined coefficients because there is no possible way that cosecant t can form from the characteristic equation. We can get cosines and sines. Well, cosecant is the quotient of 1 over sine, but that's not a possibility from our differential equations and from the characteristic equation. Because of that, all we have at our disposal is the homogeneous equation. yc is equal to c1 cosine of 2t plus c2 sine of 2t. So what we do is we say, hey, remember when we did reduction of order? We assumed that c1 and c2 were not constants, but functions. And so instead of a v times y1 or a v times y2, we're going to have two functions times y1 and y2. What we then do is we plug in the derivatives of y1, y prime, and y double prime. But there is one thing I do want to stress, that there is, when I take these derivatives, I have to be very, very careful. Because, see these two terms right here? If I take that second derivative, y double prime, these are going to be u1 double prime and u2 double prime. So in other words, I'm going to have an even more complicated form than I had before. Well, that doesn't help me at all. So what I'm going to do instead is say, look, yc is c1 cosine of 2t plus c2 sine of 2t, right? So the things in front of cosine and sine should be constants, right? c1 times cosine and c2 sine. This c1 and c2 should be constant-ish, right? So that u1 prime times cosine and u2 prime times sine should act if it's 0, right? So that's what we're going to do in order to simplify our lives. We're going to reduce this 4-item log derivative down to 2, because we're going to assume those things that should act like constants kind of do act like constants. There are other reasons why this works and why we should do this, but I want you to think like that, at least for now. Take a second derivative, and notice once again we're going to get u1 primes and u2 primes, but that's okay now, because a single derivative I'm okay with. So take y1, y prime, y double prime, and y, and plug it back into that original differential equation. Notice once we substitute in, I get terms that start canceling each other out. So the equation simplifies down to negative 2 u1 prime sine of 2t plus 2 u2 prime cosine of 2t is equal to 3 cosecant of t. But remember earlier, I already said that u1 prime cosine of 2t plus u2 prime sine of 2t is equal to 0. Well, I kind of have a system of equations. I have 2 equations and 2 unknowns. Sure, they're derivatives, but why not? So solve for u1 and u2 prime, that is. So we're going to need to solve for them. Well, from the second equation, I can solve for u2 prime. So I get negative u1 prime of t cosine of 2t over sine of 2t. Plug that back into the first equation. Well, cosine of 2t times cosine of 2t is cosine squared of 2t. And multiplying both top and bottom, well, multiplying the entire equation by sine of 2t will give me sine squared over here and sine of 2t over here times the cosecant. Well, notice I have u1s, technically negative u1s, for both terms. Factor out the u1 prime times 2, and notice I have sine squared plus cosine squared. That's 1. So, divide out by the negative 2, and I get negative 3 cosine of t. Because remember, cosecant of t is 1 over sine t. And sine of 2t is a trig identity. That's 2 sine t cosine t. So the sines cancel out, and I'm left with 6 cosine of t over negative 2, or negative 3 cosine of t. Well, that's easily solvable. But before we do, let's plug u1 prime back into u2 prime so we can solve for that as well. Okay, well, u1 prime is equal to negative 3 cosine of t. So plugging that in, I get 3 cosine of t over cosine of 2t over sine of 2t. Plugging in the double angle identities for cosine and sine, I can reduce my problem down to 3/2 cosecant of t minus 3 sine of t is equal to u2 prime of t. Well, I now know what u1 prime is equal to as a function, and I know what u2 prime as a function looks like. Integrate both of them. u1 is negative 3 sine of t plus a constant. u2 is equal to 3/2 natural log of cosecant of t minus cotangent of t plus 3 cosine of t plus a constant. Putting them back into the original equation for C1 and C2, I can reduce my solution of yt down to 3 sine of t plus 3/2 natural log of cosecant of t minus cotangent of t times sine of 2t plus C1 cosine of 2t plus C2 sine of 2t. So notice what our steps were. Step 1, find the complementary solution. Number 2, I assumed that my coefficients C1 and C2 were functions, and I tried to plug my complementary solution into the differential equation again, now of the non-homogeneous solution, but with non-constant coefficients, so variable coefficients. Step 4, I set up a system of equations to solve for u1 and u2 prime. And then I integrated and plugged it back into the form of the solution to finish up the problem. This will help us determine how this can be used in any case whatsoever. Because what happens if I have a general solution y1 and y2? Well, note from here we get the Wronskian, right? Because this is a system of equations, u1 prime, u2 prime, u1 prime, u2 prime. Notice y1 over y1 prime, y2 over y2 prime. This is the setup of the Wronskian right here. So my solution is going to be divided by the Wronskian yet again. But notice that my solution will solve for u1 prime and u2 prime. So my true solution will be the integral of y2g over the Wronskian. And my u2 will be y1g over the Wronskian. Also notice that u1 has a negative sign and u2 does not. Notice u1 prime had the negative sign due to our technique, and u2 did not. So if we remember this general formula for u1 and u2, this technique is known as variation of parameters, either by directly using this formula, which I suggest actually in this case, or by deriving it on your own. This method of plugging in functions instead of constants is known as the variation of parameters. And notice the power of this. I nowhere assumed anything about y1 and y2, p, q, and g, other than y1 and y2 are fundamental solutions, so that means the Wronskian is non-zero, and that p, q, and g are continuous. This will work every single time. The only time that this might get particularly difficult is when these integrals might get a little nasty. So be prepared. But it is doable.